we do need to learn a little bit of physics. So we're going to talk about light. So light is a form of electromagnetic radiation. And what that means is it has an electric field that's an oscillating wave, and it also has a magnetic field that is an oscillating wave. And those two waves are perpendicular to each other, but they're traveling together. So an electric field is just a region where an electrically charged particle experiences a force. A magnetic field is where a magnetized particle experiences a force. So light is one form of electromagnetic radiation. There are lots of others, but all electromagnetic waves move through space at the same time. At the same constant speed. They are moving it through time, but at the same constant speed, and that speed is called the speed of light, right? So that is 3 times 10 to the 8th meters per second. A little hard to get your mind around. 186,000 miles per second. So that's fast enough to circle the Earth 7 times in 1 second. That's really, really fast. So this is an illustration of those, This is an illustration of those waves. So here, there's the electric component, and then there's the magnetic component. They're traveling along at the speed of light. I think we all know that when lightning strikes, we see it hit, and then we hear the sound later, right? Because sound is not electromagnetic radiation. It travels at a different speed. So sound travels at a speed closer to 340 meters per second, and light is traveling at 3 times 10 to the 8th meters per second. Much, much faster. And so it is true that you can measure the time between when you see the strike and when you hear it, and you can use that to estimate how far away it was. So electromagnetic radiation is in the form of these 2 oscillating waves. And so we need to learn some terms that describe waves. So here's this wave traveling along. This is called a crest, the top of the wave. And the distance from one crest to the next is called the wavelength. It's the length of the wave. And they use the Greek letter lambda for that, which kind of looks like an upside down lowercase y. The amplitude is how tall the wave is. So it passes through this 0 line, and the amplitude would be measuring from here to the height of the crest. That's the amplitude. The amplitude is a measure of light intensity. So if you have brighter light, it has a larger amplitude. The one we're interested in is the wavelength. The wavelength, our eyes perceive different wavelengths of light as different colors. So here's red light and yellow light and blue light, and they can have the same amplitude. They're traveling at the same speed, the speed of light, right? What makes them different is the wavelength. And so our eyes perceive the longer wavelength of red light as red, yellow's in the middle, and blue is shorter. If we look at amplitude differences, small amplitude would be a dim light, and bright light would have a larger amplitude. Another thing about waves that can be measured is the frequency. And that's defined as the number of waves that pass a point in a given period of time. And frequency is this Greek letter nu, which looks disturbingly like a lowercase v for velocity. So, just watch out for that. But frequency is the number of waves or the number of cycles in a given amount of time. And so the common unit is hertz, abbreviated capital HZ, which really is just cycles per second, or number of waves per second. And when we see this s to the minus 1, that means the s is in the denominator. So the total energy of the wave is proportional to the amplitude, how tall it is, and the frequency, how fast it hits. So I like to think of this in terms of waves on the ocean. So let's pretend that we are visiting Pismo and we're standing out on the beach, right? And the waves come in. Now these are not perfect waves like we've been looking at, but they still behave similarly. And so the amplitude of the waves is how tall they are. So if a little wave comes and hits you, you're like, oh, that's a little wave, right? But if a big wave comes and hits you, it's going to flatten you. And if a tidal wave comes, it might take out half the town, right? It's got a lot more energy, right? So the amplitude tells us something about the energy that that wave has. The other thing is the frequency. So here, this is, we're getting hit relatively frequently, but what if the waves were coming like this? The water, the wave itself is moving at the same speed. When these two are moving at the same speed, this one is going to hit you more often than this one. So maybe you have, fairly decent sized waves, and one hits you, and then you wait 5 minutes for the next one to hit you, and you're like, okay, I can handle this. And then the amplitude's cranked up, and now it's hitting you every 30 seconds. Well, that's a different story, right? That's going to wear you out really fast and probably knock you down eventually, because there's more energy with higher frequency. Does that make sense? If we look at waves traveling the same speed, the shorter the wavelength, the more frequently they pass. So again, I'm going to draw bad pictures of waves. So if these are moving at the same speed, and I'm standing over here counting them, I'm going to count more of these in a given amount of time than these. But the wavelength of this one is bigger than the wavelength of that one. So the wavelength and the frequency are inversely related. If you have a high frequency, then you have a short wavelength. If you have a low frequency, you have a long wavelength. And they are related by the speed of light. So the frequency is equal to the speed of light divided by the wavelength. So wavelength and frequency are related to each other. The color of light is determined by its wavelength, which is related to its frequency. So what we perceive as white light is a mixture of all the colors in the spectrum of visible light. And the colors are red, orange, yellow, green, blue, indigo, violet. And they're always in that order. And the way I learned that, I don't remember when, was Roy G. Biv. And in my other class, I actually have a student who goes by Biv. It's her nickname. It's kind of cool. So, I just think of this as some guy's kind of odd name, Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. So when you see rainbows, especially ones that children draw, and you look at them and you're like, what's wrong with that rainbow? They probably have the colors out of order, right? And we know what a rainbow is supposed to look like, so it looks wrong, but we can't quite put our finger on it. So the way color works is, white light, like the light from the sun, it's got all these different wavelengths in it. It comes and it hits something. And that object, well, let's use this, the lid on this bottle, right? So the lid on this bottle is blue. So what that tells me is that this is reflecting light that is blue, and it's absorbing most of the other light. When something is black, like the bench top, that means it's absorbing pretty much all of the wavelengths. Something that's white is reflecting all the wavelengths. So in this picture, the girl's shirt is red. It's reflecting red light and absorbing the other colors. Okay, yeah? How does it absorb light? That's a good question. There are different ways that substances can absorb light, but basically the energy is at a frequency that sort of literally resonates with them and can cause their bonds to resonate or vibrate. Yeah, it's kind of trippy when you think about it. So, I don't know if you've noticed this, but if you had to go stand outside in the summer in July in the sun, would you rather wear a black t-shirt or a white t-shirt? A white t-shirt. Why? You won't be as hot, right? Black t-shirts just absorb all of that energy. Now, a white t-shirt is not going to reflect all of the energy from the sunlight, but it's going to reflect a lot of it, right? So there are calculations we can do relating wavelength and frequency. Here, a laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. So we're going to treat this like any other problem. We're going to go through and we're going to highlight the numbers, and we're going to highlight the question, what the frequency. So 515 nanometers, and it tells me that's the wavelength. So we just learned that the symbol for wavelength is lambda. And it says calculate the frequency, and frequency is nu, that slightly funny looking B. So we had an equation that related these. The frequency was equal to the speed of light divided by the wavelength. Maybe we don't remember what the speed of light is, but we can go look it up. Speed of light is 3.00 times 10 to the 8th meters per second. So to calculate the frequency then, we're going to take the speed of light, 3.00 times 10 to the 8th meters per second, and we're going to divide by the wavelength. Oops. Let's just redo the 5 also. Now, some of you are still not writing your units down when you show your work. Write the units down and look at them before you do the math. Here I have meter and here I have nanometers. Are those going to cancel out? No. So one thing I can do is, instead of writing the prefix nano, I can write what nano represents, which is times 10 to the minus 9 meters. Now the meters cancel out, and I'm going to be left with seconds in the denominator. So we've got 3 times 10 to the 8th divided by 515 times 10 to the minus 9. 3 sig figs, 5.83 times 10 to the 14th per second. So that's wave crests per second. We can also express that as hertz, because hertz just means cycles per second. On your calculator, my calculator shows me something like this. And we're very accustomed to just, looking at the left-hand part of the number, and sometimes we forget to check out the whole number. This E14 is the calculator language for times 10 to the 14th. And that's kind of important, right? Because 5 is a lot different than 5 times 10 to the 14th. That's really, really big. Any questions?
So the amplitude basically like potential energy per wave?
The amplitude would correspond to the potential energy. Yeah, it's definitely related to the energy, of the wave.
Because of the height?
Yeah.
Yeah. But we're not going to do any calculations where we're looking at amplitude in chemistry. We are concerned with the energy, but we're concerned with the wavelength and the frequency. So we take visible light and we pass it through a prism and we see a rainbow. That's a spectrum. But that's only one tiny, tiny piece of all the electromagnetic radiation. There's electromagnetic radiation that has higher frequency, which has higher energy, and those would be things like gamma rays or X-rays. And there are things with lower energy, longer frequencies, lower. It gets kind of mixed up in there sometimes. Lower frequencies, like radio waves or microwaves. High energy electromagnetic radiation can damage biological tissue. Things like gamma rays, not good for you, right? They have too much energy. They can actually ionize some of the molecules in your body, and that messes up all kinds of things. It's called ionizing radiation. So here is a diagram of the electromagnetic spectrum. And there's lots and lots of information on here. So there's different scales. This one is giving us frequency in hertz. So this is going from 10 to the 4th up to 10 to the 24th hertz. And this line is showing us the wavelength in meters. And this is big at this end, 10 to the 5th meters, and getting smaller over here. Because long wavelength is short frequency, low frequency. Short wavelength is high frequency. High, low, short, yeah. Hopefully you understand what I'm trying to say. One thing that students don't get about this picture. So here we have this nice, big, beautiful rainbow here, right? And it's showing us wavelengths in nanometers, 750 down to 400. This edge here does not correspond to things up here. Okay, this is coming out of this little tiny place in the middle. It's pulled out and expanded because this is what we are most interested in. But 400 nanometer wavelength does not correspond to 10 to the minus 15th meters. It's not the same. These guys are over here, right in around here. And then here is labeling the different types of electromagnetic radiation and showing you that this is the low energy and this is the high energy. So we got radio waves and microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. So there's a section in your book that has a little description of each of these things, and you should read that, because everybody should know a little bit about these. So we can use a prism to separate light by its wavelength. It will, when it goes through this prism and reflects off the surfaces, the different wavelengths will be bent at different angles. And so that's how they can get separated here. What we see from white light is a continuous spectrum, a rainbow. There's no gaps here, right? It's just continuously changing colors, very pretty. This is talking about infrared light. So this is, do you recognize that person? That's me. And this is my daughter. She's 17 now. I think she was 9. That was a long time ago. We went to NASA's, what's it called? It's down in LA. They have a really cool museum, and they work on satellites and stuff down there.
Is it the Lucas car?
Pardon me?
Lucas car?
No, I can't. It'll come to me, and then I'll share it with you. Anyway, they've got this infrared camera, right? And so if you look on the infrared camera, of course, we can't see infrared light. Our eyes don't respond to it. But we can build electronic devices that can see the light. And so the camera interprets different temperatures as different colors. And so you can see where our exposed skin is. It's more red, and back here the wall is blue. And you see my phone is very red because I was taking all kinds of pictures, right? And this is what we look like with visible light. High energy radiation is dangerous, but it can also be used therapeutically. There's a procedure called gamma knife, and what they do is they use gamma radiation, high energy radiation, to slow down or destroy tumors that can't be operated on. If you have a tumor in the middle of your brain, well, they could take it out, but in the process of taking it out, they might kill you or make you not be able to see or talk or something. It'd be bad, right? So they can't just go in there and cut it out. But this is like genius. So a gamma ray will go straight through tissue and damage stuff as it goes. So we can't just like blast that through you, because that's going to be a problem too. You've got some good stuff on both sides of that tumor. What they do is they'll take that and they'll aim it at the tumor from lots and lots of different angles. So it goes through the healthy tissue once, and then it moves. And so the healthy tissue gets a very low dose of the radiation, and the tumor itself gets just bombarded with the radiation. And then they can shrink and sometimes even get rid of the tumor. So it's really, really interesting. There's lots of really cool stuff about radiation. So waves can interact, and when they interact, it's called interference. And you can have constructive interference and destructive interference. So constructive is building up. So if the waves are in phase, so here where this crest lines up with that crest and this trough lines up with that trough, when these two waves get together, they build on each other and their amplitude becomes larger. It's constructive. If the two waves are out of phase, where the peak of one is lined up with the trough of the other, and they interact, then they cancel each other out. They destroy each other. It's destructive. It breaks them down.